tonight, nonparametric tests of significance. What we've done thus far with T and with F, those were what we call parametric tests. They meet specific parameters. We require normality, meaning a large sample. We have to have interval level data. That doesn't always happen. Sometimes we have small samples. Sometimes we have ordinal or nominal levels of data. So we can't run T and F. We run what we call non-parametric tests because they don't stick to those parameters. The one we're going to talk about tonight is chi-square. I understand that looks like chi. That is chi. Chi-square is the one we're going to be talking about tonight. Chi-square is what we use when we have skewed data. When that curve isn't a perfectly symmetrical curve, when it's leaning one way or another, we use chi-square if we have a small number of cases. We use chi-square if we have nominal or ordinal levels of measurement. Chi-square relies on a bivariate table. Bivariate, two variables. Remember this from early? Yes. Okay. Going to break this down and show it to you. All of your tables have to have a title so people know what they're looking at. Your cells on these tables are an intersection of your rows and your columns. Subtotals on the ends are called marginals. And N is the intersection. I understand that kind of sounded like a foreign language just now. It's cool. We're going to break it down and talk about it. Here's the bivariate table. Doesn't look as scary in person as it did when I was just explaining it. We have to have a title. We need to know what we're looking at. So here we're looking at rates of participation in voluntary associations by marital status in senior citizens. Marginals are these numbers on the ends and on the bottom. We had 50 people with high participation, 50 with low. We had 50 people who were married, 50 people who weren't. These are our marginals. So looking at this data, what's our independent variable? Are we saying that your marital status will influence whether you volunteer or not? Or are we saying your volunteer status will influence whether or not you're married? The latter. Volunteer status will influence whether or not we're married. Cass, you're shaking your head. What do you think? Marital status will influence whether or not you participate in voluntary organizations. So we're saying marital status is our independent variable. Volunteer status is our dependent. Note the marginals. 50 with high, 50 with low, 50 that were married, 50 that were unmarried. What's our total number of cases? How many people did we ask? What's our N? 100. Yes, that's what we're saying at the intersection. The 100 right here. 100 people total. Okay, your columns in a bivariate table are your independent variable. I know that's a question you need to know, so you may want to make notes of it. Column is independent variable. Rows are where your dependent variable goes. You will have as many columns as you have choices for your independent. You will have as many rows as you have choices for your dependent.
Can they be even?
Yes. 2 choices and 2 choices, 3 choices and 3 choices. Is that what you're asking?
Yes, ma'am.
Yes, they absolutely can be even. How many cells you have for a chi-square depends on how many choices you have in your independent variable, how many choices you have in your dependent variable. If you're a visual person, hopefully this will make more sense to you. Column is our independent variable. So we're going to put numbers for the columns here. Rows are dependent variable. So we're going to put numbers for the rows here. We add everything up and we find our total N. Do you understand where each of the cells are coming from? Cell A, cell B, cell C, cell D? Yes or no? Yes or no? I know you're tired. Yes. We're okay with this? We understand where these are coming from? Thank you. All right, so let's take a look at a chi-square in action. Here we're looking still at marital status and participation rates. How many people were married and had a high participation rate? How many people were married and had a high participation rate? 25. How many people were unmarried and had a high participation rate? How many people were married and had a low participation rate? And how many people were unmarried and had a low participation rate? 25. Not hard to read. We can do this. You got it. All right, so here's what chi-square looks like. And I know in the back it's hard to see. It looks like an S. This is going to be your chi-square. Chi-square is based on frequencies. Remember frequencies from the earliest part of the term? F. We're still dealing with frequencies. We have FE and FO. FO is our observed frequencies. The number of people that actually fit into each of the blocks that we observed. Our expected is how many we would expect to fit into each of those boxes. So chi-square is based on our observed and our expected. Null hypothesis for chi-square is the same as all the null hypotheses. We're saying things are equal. This time we're saying the frequency of observed is equal to the frequency of expected. Our research or alternative would be the frequency of observed is not equal to the frequency of expected. So the rules are still the same. Instead of dealing with means this time, we're dealing with actual frequencies. Our observed frequencies and our expecteds. Here's your statistic. Chi-square is based on, and again, I know in the back that may look like an X, so here's what it actually is. Here's chi. For every cell that we have, we do frequency of observed minus frequency of expected. We square it, and we divide by the frequency of expected. Once we do that for every cell we have, we add it up. And there's our chi-square statistic. Nothing new in this. You've done much harder problems than this. Expected, though. How do we find out what's expected? That's this formula. It's our row marginal times the column marginal divided by n. Our degrees of freedom for this problem, row minus 1 times column minus 1. Okay, let's see what this looks like. This is another one of those tests where you're never going to do it by hand, but I'm going to show you so that you know what it means when you read about it. Here we're looking at social workers. We're looking at accreditation status. Was their school accredited or not accredited? And are they working as a social worker or working in a different field? All right, how many people went to an accredited school and are working as a social worker? 30. Fantastic. How many people went to a not accredited school and are not working as a social worker? Not accredited, not working as a social worker. 35. There we go. Here's our row marginals. There were 40 people working as social workers, 60 that weren't. There were 55 people that went to an accredited school. There were 45 that went to a non-accredited school. How many people did we have total? How many people did we ask? What's our N? 100. Perfect. All right. Our null hypothesis. Accreditation and employment observed will be equal to the expected. Research or alternative, observed in accreditation and employment, will not be equal to expected, accreditation, and employment. Making sense? Null is the same. Research is the same. We're still dealing with equal and not equal. All right. Here are our observed. There were 30 people out of these 100 that went to an accredited school and are working as a social worker. 25 went to an accredited school and are not working as a social worker. 10 went to a non-accredited school and are working as a social worker. 35 went to a non-accredited school and are not working as a social worker. Observed numbers. Expected. Remember, for our expected, row marginal times column marginal divided by n. So for cell A here, row marginal 40 times column marginal 55 divided by our n of 100 should give us 22. Got your calculators out? Grab your calculators or phones. Let's figure out the rest of these. What's our expected in cell B? Row 40 times column 45 divided by n of 100. $18. Everybody find it? Yeah, okay. How about cell C? Not working as a social worker that went to an accredited school. Row 60 times column 55 divided by 100. What's our expected there? 33. Excellent. Last one. How many people went to a non-accredited school and are not working as a social worker? Row of 60 times column of 45 divided by 100. 27. Fantastic. That wasn't so bad, right? Okay, let's put it together in the formula. For all four cells, we had cell A, cell B, cell C, cell D. For all four rows, we have our observed. Okay, minus our expected. So cell A, 30 was our observed, minus 22 is our expected. Cell B, 10 observed, minus 18 expected. Cell C, 25 observed, minus 33 expected. Cell D, 35 observed, minus 27 expected. Okay, we've done the math. Subtraction's easy. We come up with these numbers. Now we square them all. 8 squared, negative 8 squared, negative 8 squared, 8 squared. Okay, not so bad. Last step. For all of our squares, we divide by the frequency of the expected. So we have 64 divided by 22. 64 divided by 18. 64 divided by 33. 64 divided by 27. That's where we're getting these numbers from. With me? That's it. We add it all up. We have a chi-square of 10.78. That's our chi-square statistic. If you'd like to look in your book, see what we do with that, you've got a chi-square table. I've got it up here if you don't want to pull your book out right now. We always work with an alpha of what? 0.05. Thank you. Degrees of freedom, row minus 1 times column minus 1. We had 2 rows, so 2 minus 1 is 1. We had 2 columns, so 2 minus 1 is 1. 1 times 1 is 1. We're working with a 3.84 as our chi statistic. Do you all see it at the top of this? At the top of the column, 3.84. Okay, we came up with a 10.78. Our critical chi-square is a 3.84. What do you think we're going to do with the null hypothesis? Calculated's larger than critical. Do we reject or retain? We reject. Same rule as T and F. Calculated is larger than critical, so we reject. Calculated smaller than critical, retain. Okay, let's put it all together. We always use an alpha of 0.05. Your degrees of freedom on this one are a little bit different. Row minus 1 times column minus 1. Rules have stayed the same. Same as T, same as F. Calculated larger than critical, reject. Calculated smaller than critical, retain. Do you have the theoretical ideas behind chi-square? Yes, no, I understand it's a time change. Retired? Okay. Chi-square you will never in a million years do by hand. You could. It's not a terrible one. You won't. I'm going to show you SPSS in a minute, but let me go over some rules of chi-square really quick. First of all, chi-square is really popular because you can do it with a lot of things. You can do it with nominal. You can do it with ordinal. You don't have to have that interval level of measurement like we do for our T-scores and our Fs. So it's a lot easier. The test has less demands. You'll see chi-square a lot in the literature. Sample size is extremely important though. This is in red because I want you to understand this. If you have a cell with an expected frequency of 5 or less, back up. You cannot do a chi-square test. It will not work. Your results will be wanky, for lack of a better word. So if you have expected frequency less than 5, you need to recruit more people to ask, or you need to pick a different test, or you need to collapse some categories until you get expected frequencies that are over 5. So that's important. Expected frequencies of less than 5, stop. Look, pick something else to do. Ready for SPSS? Yes, we like SPSS, right? Yeah, it's a world easier. Okay. Here is a chi-square statistic in SPSS. Lot of stuff up there. 2 really important things for you. First of all, down here, it'll tell you if you have any cells that have an expected value of 5 or less. The chart will tell you. You don't even have to figure it out on your own. That's awesome. We have no cells with an expected value of 5 or less. Cool. Let's proceed. Here's all the statistics. Important one for us, Pearson chi-square. That's what we're looking for. We don't care about anything else. We know on SPSS we're looking for sig, right? That's important. Our friend sig. Okay, we're always looking at sig to the right of the degrees of freedom. We have a 0.693 here. 0.693. Smaller or larger than 0.050? Larger. So what do we do with the null? Retain or reject? Retain. Yes. Sig greater than 0.050, we retain. Sig less than 0.050, we reject. We would retain this null. We don't know what the test was, but we know observed and expected are equal.
Question.
Yes.
What if the sig is the same? What if it's the same? Can you accept
I'm not sure what you're asking.
0.5 or whatever? Would it be the same if it was the sig also?
If the sig on here is 0.050, yes. If it's 0.050 or lower, we reject the null. If it's higher than 0.05, we retain it.
Well, what if it's the same?
What about this one? For those in the back that can't see this teeny tiny chart, we're looking at Pearson chi-square. Sig to the right of the DF, we have a 0.000. Reject or retain the null. Already heard it. What are we doing? We're rejecting. It's a good day. Here. Sig to the right of the degrees of freedom. Pearson chi-square, 0.485. Reject or retain the null. What is it? Retain. Fantastic. That's higher than 0.050. We retain that null. So in summary, we've made it through the basics of chi-square. That wasn't so terrible, right? In summary, parametric tests are your T, your F, your Z, what we spent so much time on earlier in the semester. They don't always work. If you have a small number, if you have a nominal variable or an ordinal variable, we can't run those tests. That's where our nonparametrics come in handy. Chi-square is the main one that you will see. It's the main one that you will use. It's the main one that will show up in your literature. Remember that chi-square is based on frequencies of observed and frequencies of expected. It's still a test for independence or significance like the T and the F. It's just based on frequencies instead of means, because we know nominal and ordinal can't have means, right? They don't go in order. They're not true numbers. They're not interval. They can't have means. So we run with observed and expected frequencies. Questions on chi? No? We're good? Okay.